everyone, welcome back to my channel. It has been a long time since I've uploaded a video. I've been busy with job and life things, and I think finally I'm in a state where I can go back to video making. So hopefully some of you return and watch this new content. For the past 2 years I've been working in the LLM space, building models and so on. And recently I've been interested in getting into the multimodal LLM space. So in this new series, just as a way to teach myself how MLLMs work and so on, I will try to build an MLLM from scratch. So we'll just start with paper review and then just start to implement. We'll see where we get, but that's the plan at least. So multimodal language models, as you know, are just language models that can deal with your inputs of different modality. So they can be text, video, images, audio, and so on. At least from a perspective of this playlist, I will just try to combine text and vision being just images, not even videos, but we'll see where we get. GPT-4, as you know, has a multimodal version and it does pretty well. So for example, it can input images here and it can describe what is in the image and so on. So it's pretty much the state of the art of what multimodal language models can do. So that's pretty impressive. And I came across this benchmark, or rather a leaderboard, which kind of ranks what are the best language models using one of the Llava models as a baseline, like how much better you are on top of that model. And GPT-4 near the top. I think the latest Claude model outperforms it, but they're more or less at par, I would say. So we will see where we get. The end goal here is to compute these metrics, and we will see where our model lands. I'm guessing it'll be below 21, but so the way people typically approach the MML or MLLM space is by projecting everything into the language model space. Like, we know language models very well, and we've been teaching them to give generative output for quite a lot of years. So and we have a lot of backbones for these language models, which are hundreds of billions of parameters. So the idea is that if we can project all the different modalities into the language modeling space, then it kind of becomes uniform, and we can take advantage of all the things that we've built for language to parse these new modalities. And there are two main papers that came out recently being 2023. One is MiniGPT4, and the other one is this visual instruction tuning paper. So MiniGPT4 is kind of taking cues from I guess Karpathy's MiniGPT. We'll get into it, but this visual instruction tuning is basically this Llava form of models. So in the MLLM world, you will see this Llava family of models, or Llava recipe for training the models. And this is the paper that started it all. Both the techniques are pretty much similar. At a high level, both are similar. So I will just review the MiniGPT4 paper, but I believe this Llava paper goes into details about the data that you want to train the model with, and how do you align both the vision and language data sets together. But since we are just starting off, we wouldn't worry about data right now. We just want to get a sense of what the architecture is. So I'm going to skip this paper, and I will just quickly review what MiniGPT4 architecture is. Llava architecture is similar, but just to get into the details. Oh yeah, I also wanted to give you show you a demo of these models. I couldn't find MiniGPT4 demo, so I'm just going to show you a Llava demo. Here I open this webpage, MLLM.org, which basically has a leaderboard and a chatbot arena. It also has some vision models. The selection is kind of low, but let's see. So they only have, I believe, the Llava model family. So let me upload a picture and show you how this works. Okay, so here I have a picture of Black Canyon from Gunnison, which is my favorite national park in Colorado. And let me ask, what do you see in this picture? And now we wait because inference takes time. Okay, it has identified that there are canyons in this image, which is pretty cool. No, not the craziest thing, but pretty cool that it identified canyons, and it's just giving you, the sky is partially cloudy, right? So it understands everything. Let me see if it can identify the location. Probably not. Okay, it got that wrong. But this could be an image from the Grand Canyon, although its Grand Canyon isn't this green. So your mileage will vary. All right, so let's get into this paper. Now, the key thing that this paper proposes is there has been a lot of research done, a lot of good foundational models in vision. There are a lot of good foundational models in language modeling. So instead of training a new foundational model that does both vision and image together, we should make use of these two separate language model and vision model and somehow try to combine them together. So the idea here is they try, they have a frozen encoder, which is the vision model, and a frozen LLM, and they try to project the vision space into the language modeling space using a projection layer. That's the key idea, and I'm sure they have their code. We might go through the code at some point, or we might use our own custom implementation. I haven't given it a thought how we will go about implementing this model, but sky's the limit. It's a simple read, but here is the main architecture of their paper. So the language model that they use is Vicuna, which is, I believe, which comes from the Llama family, which is a fine-tuned or instruction-tuned version of the Llama family. Note, this is frozen. And then they have an image encoder, which is VIT-based and has a QFormer module. So I will quickly describe what QFormer is, but you can just take this to be an image encoder. I believe you can just replace QFormer and VIT with ResNets, and I think things should work the same. Maybe the performance difference would be low, but it should be the same. And then you have a linear layer, because whatever hidden dimensions that you finally output needs to be, so its distribution needs to be translated into the distribution of the language model, and that's where the linear layer comes into play. And then this is these soft embeddings are encoded into Vicuna, and then you have You can give some text input as well. You have some image input, and then it will describe whatever image that you are trying to describe, or ask a question about that image, or any of that. So that's the rough architecture. The only thing that you train is this projection map. Well, that's the major chunk that you need to do. You might want to just slightly update the weights of these frozen models a bit, but we'll get to it. So from my point of view, what I was thinking is I want to see the opposite end of the spectrum. How small can we go in terms of the language model and the image encoder? So Vicuna is based off Llama, so that's still like a 7 billion parameter model. And recently Microsoft came up with the Phi-3 family of models, which are around 3 billion. So maybe we can like try Phi-3 and some very lightweight image encoder and see where we get. I know, just something to aim for. Okay, so yeah, so here they say that this the visual module is a component from this BLIP2 family of models and has a Q-former network. And then they add a single projection layer, so it looks like a single fully connected layer that maps it to the language modeling space. And we see that it is trained for 20,000 steps. So 20,000 times 256 data samples or forward passes on 4 A100 GPUs. So, you know, if you try with a smaller model, we can cut back on this budget, but we'll see. Okay, so let me describe what Q-former is. So for this, we will have to open the BLIP2 paper, and I will give you like a brief idea for the details. Please read the paper, but I don't think the details are that important. So Q-former is this, basically this block. So, okay, first you have an image encoder. Now this is your box standard VIT, the vision transformer, or it can be a ResNet or anything. So you give an image which is patched up, and it goes through the encoder, and it will generate, you know, an embedding. Now you have two transformers, or rather two layers of decoders, or rather two layers of like attention modules. One takes in text, and one has just takes in some random queries which are learnable. So these are the parameters that will change. Backprop will flow to them, and they will update. So they are just, you know, some learnable queries. We do not update, like this is not an input to the model. This is what the model will learn. And so there are two transformers because there are two sets of attention. The first transformer has self-attention on these queries, and it has a cross-attention which takes in the query from the image encoder. So that there's a cross-attention there. And then feed-forward layer, while the second transformer module works only on text. So given a text, it has self-attention, and then it does the feed forward, and then it's your box standard decoder. Okay. Now these two blocks can be completely separate, or their attention modules can be combined to make a giant self-attention that spans both these learned queries and the input text. The reason for doing so is if we can keep it separate, or if we combine them, we can compute three kinds of losses. So the first loss is, so given an image and given a caption, can we do an image text matching? Does the caption align with the image? So this is like the clip loss. We can do text generation. Given an image, can we generate text, like generate the caption? And just somewhat like clip, we can do contrastive learning. You know, similar things, closer dissimilar things further away. So, so these are the three losses that we can compute. I talked about this self-retention module that can be combined or separate. So so on the right side, we see some examples of that. So if I'm doing image text matching, it's combined. So nothing is masked. T here are text tokens. Q is these learned queries, and you can see nothing is masked, so it's one giant attention. If we are doing image text contrastive learning, we compute the embedding separately. So it's like these two are completely separate transformer modules, and hence the masking, and then you compute all of your attention stuff of Q separately, for the text separately, and then just do the loss. So here they are treated separately. And if it's about generation, you just need the causal mask on the text side. So this is kind of how it is. Again, the details are somewhat not relevant because so our starting point would be these pre-trained modules. So we don't need to worry about the training, but it's still good to know what the inner workings are. And now when we actually deploy these things, we will, depending on how you want to use it, the QFormer module will be the first transformer, the image one, and this encoder together. Or it could be this whole thing, but for our purpose, it will just be this first transformer and this image encoder. So that's this QFormer module. I'm not sure if I want to use QFormer. We will see where we get, but we can just maybe to start off, we can try with ResNet and something similar, something simple, or just base VIT as well. Okay, let's go back to the MinGPT paper. Okay, I just paused the recording and I went back to check the audio. I see there's a bit of static in the background. I apologize for that, and I'll try to fix it in the next videos. So apologies. And also I realized I typically used to start the video with a beer in hand. I don't have it, but I do have coffee. From next time, I'll fix that as well. Okay, great. So what they see is here, that in their experiments, they see that just doing this frozen language model, frozen transformer training of just the linear projection, they are able to get similar results as GPT-4. Of course, they won't be identical because GPT-4 is a much larger model, and we don't know what their training recipe is for these multimodal capabilities. But this MiniGPT gets us somewhere closer to what GPT-4 does. Okay, now one key thing is how they train the model. So that's what I want to hone in on. So first of all, they do a two-stage training process. And the initial stage involves pre-training the model on a large collection of image text pairs, so to acquire vision language knowledge. And so that means is they start with a database of image and the captions, or image, their descriptions, something like that, like aligned stuff, and they would do quote unquote their version of pre-training on that. And then they will fine-tune, finally, in the second stage, they will fine-tune with a smaller but higher quality image text data set. So kind of the data set, if you ignore the quality aspect, is similar between the two stages. Now what is different, and it's not mentioned in this paragraph, they mention it later, is in the first stage, we only train the projection layer. However, in the second stage, we fine-tune everything. So, okay, let's get into that. Now, as I said, so this projection layer is like a soft prompt for the LLM. So soft prompt here means it's not in the vocabulary space of the tokens of the language model. However, we directly interact with the embeddings. So note, in a language model, your input is text, which is then tokenized, and then each token is mapped to an embedding, right? Because these embeddings are learned during pre-training, so each token, like Sunny, gets encoded into a hidden dimensional space. So what soft prompt here means is we directly plug into that hidden dimension space instead of going through this vocab tokens, because vocab tokens kind of don't make sense when you translate from image to this language model. Although, now that I think about it, it might be interesting to see what if we were just mapping to this vocab token space. What would the images be? Because there would be a lot of information loss for sure, because vocabs are like what, 50,000 compared to hidden dimensions, which, like, let's say even if the dimension is 512, because each of these elements can be from -1 to 1 or whatever the range is, it can capture a lot more information than just 0 to 50,000 integer. But we'll see. Something to, it's a fun thing to try. Although I think it's completely stupid. But okay, so like I said, throughout the entire pre-training process, both the encode image stuff and the LLM is frozen, and only the linear projection is pre-trained. And what they go over 20k training steps on 5 million image text pairs. So this bit is interesting to me, because you're really training a projection layer, which maybe is one fully connected layer or a few fully connected layers, and it requires this much data to align. Yeah, that's just interesting. Okay, and so what they see here is they get, I guess, some decent result, but they observe instances where the language model is producing gibberish. So intuitively what could be happening is just with a projection layer, it is hard to, because the modalities are so different, it is hard to align exactly the distributions, the image modality into the vision modality. It's a bit hard. So now in stage 2, what they will do is fine-tune everything together so that now the misalignment can be corrected between these distributions. And that's what they do. So there's a section about how they get this high quality data set for stage 2, and what are the prompt signatures they used for this alignment. So they have an image tag, image feature, and then close image tag, and then text, because they're doing it in a chat setting. That's why you have these human and assistant tags. Okay, again, those are details that, because we only care about the architecture at this point, we will skip over those details. Yeah, okay. And then finally, they fine-tune everything together on this higher quality data. And note, the fine-tuning, you don't need a lot of fine-tuning. You only need a tiny amount so that you get the distributions to align completely. And it only takes them 7 minutes on a single A100. So in our experiments, I think we can also maybe try LoRa and any of these parameter efficient techniques to do this quickly, because I don't want to be spending thousands of dollars on training these models. But yeah, and eventually, once they do this, their results are pretty good. As you can see, help me write an advertisement for this. And I won't read the output here, but you can check it out in the paper. Pretty good. So eventually, turns out to be pretty good. So I think, yeah, that's pretty much all I wanted to cover in this video. The high level architecture of this multimodal language models. I mean, right now we are only talking about 2 models. Technically that's multi, but it's more like vision language models, but details. But this is the kind of architecture that we will be implementing, and we will try to get it bit by bit and see where we get. Okay, yeah, that is what I wanted to talk about for this paper. I will link the papers down, both this one and the Llava paper. Yeah, before we end this video, let me just take a look at the GitHub repo that they have. I haven't looked at it before, so I might fumble through some things. Let's see, I just want to check out what was that training code. So I guess we'll have to go through this. And let me see if I can find something. Training relate. Oh, for the life of me, I can't spell today. No, not here. Like so I want to see if they were using deep speed, like what was their distributed, because models this big you cannot train on a single GPU without LoRa, so you would have to do it in a distributed way, and there are multiple frameworks available for doing distributed training. And my bet here would be that they're using deep speed, but I don't know. So there's training config, so we can just quickly take a look at it. This does not tell me anything. Let's go here. Maybe I won't be able to find it. I'll have to there's a train.py here. They might be just writing their own implementation of torch distributed, because it's not too complicated. So yeah, that's okay. We can also look into deep speed just to make our job easier. But okay, I think yeah. So as we build this playlist out bit by bit, we will be implementing different things, and I'm excited to as to where we land up. All right, thank you so much, and I will keep uploading at a regular cadence, and I hope you keep coming back to watch these videos. Thank you so much.